It's so nice to see you. Hello, my name is Antonia, and this is my friend Xavier, and we want to talk to you about Kubernetes at the Edge today. We're also going to show it to you in action. Let's all hope that it will work. So we're going to start with a bit of an introduction to edge computing for those of you who may not be that familiar yet. And then we want to talk about how it is used in the industry today. And we will dive into a specific project, which is called KubeEdge. And we will look at the architecture, and then we're going to demo it for you. So after the demo, we want to anchor everything a little bit back to the real world, and hopefully we can have a little discussion at the end. So edge computing, what is that? According to Gartner's glossary, edge computing is part of a distributed computing topology where information processing is located close to the edge, where things and people produce or consume that information. Now, how does that look like in practice? If you take a little look at the slide here, you can see a factory at the bottom, and then you can also see a couple of clouds. A factory can be a place where information, obviously among other things, is produced, or some sort of data. And usually the machinery that produces this data in a factory will be things such as sensors, or robots, or other machines that are used in the factory, and we can refer to these as IIoT devices. And IIoT stands for Industrial Internet of Things. Now, traditionally, all this data produced by our devices is going to go up to the cloud, right? However, this can be extremely slow sometimes, or it can be very expensive, and also sometimes it can be impossible. So in that case, we introduce this additional layer which is between the device and the cloud, which we refer to as the edge. You can see the edge here in green, and you can see a couple machines in there as well. And you have to think about these as servers which are placed within the network of the factory, so they are physically close to the machines that we're working with. Now, why would you want to do this? There are a couple of reasons for this, and here's 4. So the first one, latency. So if your edge device is a self-driving car, for example, you don't need any latency, right? You need to make really quick decisions. Then you also have bandwidth problems. So if you have a lot of raw data, it can be beneficial if you pre-process it somehow and then later have less data that you have to stream to the cloud, right? Now, there's also the problem of autonomy. So your factory could be in a very remote location somewhere, and the network can be very unstable sometimes. But obviously, if your network is down, you still want everything to work just as usual and just reconnect when the network is back. Then there's also privacy issues. So maybe some data you just don't want to put into the cloud, right? Or there can be some legal reason why you cannot do it, or some user trust. And all of these can be reasons why you want to keep this as close as possible to your machines. Let's look at some examples of fields where this is already happening. IIoT, which I've mentioned, retail, smart cities, telco, healthcare, space. Of course, this is not an exhaustive list. There's new fields added daily. And let's now take a look at how Kubernetes fits into all of this.
All right, thank you. So we had a look at edge computing, and now let's see why we might need Kubernetes at the edge over there. So there are a number of challenges when we work with edge computing. And the main ones are scale, connectivity, and updates. So working with edge computing is different than working with data centers or cloud. You will have to scale to thousands of small nodes and devices, usually scattered across remote locations. And these locations, as we already mentioned, are often resource constrained. They can have bad connectivity, and these devices might remain offline for a period of time. However, we still need to be able to patch our devices consistently and keep them updated. And Kubernetes already solves most of these challenges in traditional IT environments by being declarative, as you know. So you have a declarative API, you specify a desired state, the system will make it real. It is portable, as in you can run the same applications, whether you run in the cloud or at the edge, in our case. Automated through the use of reconciliation loops in controllers. So we reduce manual operations for our operators. And you get the same familiar Kubernetes API that we already know and love. However, Kubernetes assumes stable networking. So it is often the case in cloud and data center environments, but at the edge it's not always true. And this is where KubeEdge comes into play. So KubeEdge was started in 2018 by Huawei in China, with the stated mission to extend Kubernetes at the edge to edge nodes and IoT devices. So the main features are to handle unreliable connectivity, management of devices through the use of device twin, which we'll talk about in a little bit, and use the standard Kubernetes API. So pretty much the same things we just talked about in the challenges. So it was entered in CNCF actually in 2019 already, in March, where it was sandboxed, followed by a V1 release a few months later. November of 2020, we got incubating states, and last year in October, KubeEdge graduated. So it is already pretty mature, and the community is already using it pretty extensively. And I wanted to share a couple success stories of KubeEdge. Like the first one was in China, I think in 2019, with the overhaul of the electronic highway toll collection system across 85% of the country. So originally you would have like toll plazas like we have in Europe, like we used to have with humans collecting fare from cars. This system was replaced by overhead gantries with like cameras that do like license plate recognition. And this system is running on 100,000 KubeEdge nodes, running 500,000 applications. And just to put this into perspective, it generates over 300 million data points every day. So quite a scale for an edge project. And this is said to have improved traffic efficiency tenfold in terms of speed and reactivity. And the next big one is pretty cool, in my opinion. The first cloud native satellite, I guess, is kind of the big ticket item here. So the application was the prevention, like flood prevention and disaster mitigation. So originally, you have your satellite, it images an area. That picture is stored on local disk, then transmitted downstream to the local station. And a human will compile a report based on that information. However, in some regions, usually in the mountains, you can have a cloud cover. So you still take the picture, you still transmit it, but that photograph is useless. So you've wasted bandwidth, and you've wasted time at the same time. So in 2021, China launched the first cloud native like KubeEdge satellite. And these satellites embed like a small AI model. So when the zone is imaged, that photograph is run through this AI model. It will identify the cloud cover, it will identify the water levels, and based on that, it will determine whether this image is worth transmitting downlink. If it is, there is a more powerful model at the ground station that will process this data in an automated way, so you don't need like humans to do that stuff. And it's said to have reduced disaster response time by from days to hours, and the data transmission by around 90%, which is kind of significant when you take into account like downlink quality in satellites. So that was a pretty interesting one. If you want to know more, like there's more case studies on the public website, kubeedge.io/case studies. There's quite a few, but these two ones were the pretty significant. So I'm going to give it back to Antonia for some architecture.
Nice. So this is the fun part where I'm going to show you some architectural drawings. Before I'm going to go into any sort of detail, I want to just show you a little higher level view of what KubeEdge actually looks like on your cluster. So you may recognize this cloud edge device trifecta here from the earlier slide. And one thing I want you to pay attention to is that the cloud layer here does not mean a cloud provider. It means any Kubernetes cluster, basically. So this can be an on-premises cluster as well, okay? So the first component that you can see here is the Cloud Core. So the Cloud Core is the only entry point from the Kubernetes API into the edge. And all of the communication between the edge and your Kubernetes cluster will go through the Cloud Core. Then on the edge layer, you can see the edge core. And one edge core runs on each edge node. So you can see only one here, but just imagine there can be thousands of them. And again, as Xavier said, those could be satellites or tall stations or something else. The edge nodes join the Kubernetes cluster by connecting to the Cloud Core. And they look like a normal Kubernetes node. So there is a specific label on it, so you can schedule your workloads and everything. And the edge core is installed to the machine as a single binary. The edge core talks to the device layer via MQTT, and it can also talk to local APIs or apps via HTTP. On the device layer, again, you will have your robots, machines, all these things. And KubeEdge also has a framework where you are able to represent these machines as Kubernetes custom resources. As a side note, I have actually marked all of the Kubernetes API-related streams here in blue on these slides, and the ones that are related to devices in red. Maybe that is going to make things easier to follow. I'm not sure, you tell me. But let's first look at the Cloud Core. So the Cloud Core is installed as a Helm chart on your Kubernetes cluster, and there is an upstream CLI tool that you can use to do that. It's called KeyADM. It also does a couple other handy things. The Cloud Core has a few components, and the first, which you can see here, is the Cloud Hub. And the Cloud Hub is a messaging broker which keeps open a secure, persistent channel to each of the edge cores, and it does so through WebSocket or Quick. There are a couple of controllers in here as well. You can see a red and a blue controller again. The edge controller, that is the blue one, it propagates changes to workloads running at the edge from the Kubernetes API to the edge. And then in the opposite direction also reports back things such as statuses and events and so on to the Kubernetes API. The device controller, which is the red one, reconciles device CRs, which are the custom resources I was referring to earlier. This syncs between Kubernetes custom resource and any managed devices. And as I've mentioned, all of the communication is bundled through the Cloud Core like this. And this has a couple of benefits. Now, the first one being load reduction, and this is achieved through aggregation of updates. So it does not actually send all of the messages from all of the edge nodes to the Kubernetes API, but it aggregates them so as not to overload the API server, right? Then it also guarantees resilience across flaky networks, and this is done via incremental updates. So in case your node disconnects and then it reconnects later on, it's not going to flood, like spam the Kubernetes API again. It will update incrementally. This way you can actually integrate Edge into an existing Kubernetes cluster, and you can, I think you can add up to 100,000 nodes like this. It has been shown, I think the benchmark was 100,000 nodes for a cluster, which is a lot. Now, let's talk about the Edge core as well. The Edge core has a memory footprint of around 70 megabytes. And the Edge core also has an Edge hub. So this is the counterpart to the Cloud Hub. It links to the cloud through WebSocket or Quick, as I've mentioned, and it will route all the traffic from the cloud to the correct Edge modules. It also reports the node and device status back to the Kubernetes API and handles such things like keep alive, routing messages within the Edge, and so on. You can see here two important modules that work with the local state. The first one is the meta manager. This is a cache and message processor. This stores data like pod state or config map contents and so on in a local database. This is a lightweight SQLite database. And this is so that your Edge node can still function when it's offline. And then later, changes are going to be synced to the cloud. The other component here is the device twin. This one keeps track of the state of devices, and it manages attributes and status. It will sync that information to applications that run locally, but it also syncs it to the cloud. Now, on the lower left here, you can see a little guy called EdgeD, and you have to think about this one as something like the kubelet of your Edge core. So this manages lifecycle of pods, talks to container runtime, and ensures that you can run your workloads on the Edge node just as you would in a cloud node. All of the communication that is happening at the edge goes through this common communication layer, which is unique to KubeEdge, that is called Beehive. So on top of the Beehive, you get 2 buses. The first one is the event bus. This integrates with the MQTT broker, and it connects edge modules and device mappers, which in turn connect to actual devices via device protocols, which is something that we're going to look at later. Then the service bus provides HTTP communication with local apps and APIs. You can also see here the container runtime, which runs pods under the control of EdgeD. And you can see the mapper, which, as I mentioned, is a translator between device protocols and KubeEdge. All of these components here taken together will allow edge nodes to keep running workloads and manage devices even when the cloud connection is very unreliable. Let's talk about devices.
All right. So at this point, we've talked about having an edge node in our Kubernetes cluster. So this is what we've done, and it is already a very valid use case of KubeEdge because you can schedule workloads at the edge, which is good. But we can go a little bit further than that by leveraging the device capabilities of KubeEdge. So this is where we get into the IoT territory. And here it's all about protocols. So we are talking about communication protocols. These are used to standardize how data is collected, transmitted, and exposed for our consumers. So an IoT device is basically just a thing that generates data. So it could be various sources like cameras, sensors, bunch of things you could have around in a factory floor. And these are exposed on specific industrial protocol usually. But think of it as like an IKEA temperature sensor that you would get in your home that you connect to Home Assistant via a Zigbee dongle. Same thing, except here that data, we want to consume it in KubeEdge. And this is where mappers come into play. So a mapper is a translator between the physical world and the KubeEdge logical world. And in the industry, they are often referred to as adapters, like HiveMQ Edge, for instance, call them that. But in the case of KubeEdge, they are called mappers because they map a specific protocol to something that KubeEdge understands. And these mappers can be visualized here a bit more clearly. On the right-hand side, you have your hardware devices that will generate the data, sensors, cameras, etc. And on the left-hand side, we have KubeEdge, which is where we want that data to go. So the mapper is in the middle. It knows how to talk to these devices, and it will convey the data back to KubeEdge via the messaging protocol that Antonia explained already. So here we have 4 mappers, one for each of these protocols. There are a bunch already available upstream. If you go on this repo here, KubeEdge/mappers-go, there's quite a few like Modbus, OPC UA, OnVef, GIGO, something like that. There's quite a few, but if you need to make your own, there is a framework to build them. It's written in Go, and there's pretty good documentation on how to do it yourself. So once you have your mappers, we need to represent those hardware devices in Kubernetes. And this is where those custom resources come into play. So there are more custom resources when you install the Helm chart. But these 2 ones are interesting for us today. So the device model is the physical model properties of our device. So kind of think like a Philips Hue light bulb model X, and then the device instance is the actual thing that you will deploy somewhere on your factory floor. I say factory, but it could be a train, a car, a plane, or whatever. But in this case, it would be the light bulb that you install in your living room, so the actual thing. So these 2 CRs are what we use in KubeEdge. And for a more industrial example, we have this Advantech Adam 6017. I've never touched or even seen one of these. I just Googled for a simple device for the example. It has 8 channels to which you would connect sensors. You can see the little red, green things where you would connect your input. These are mapped to Modbus register addresses. It is compatible Modbus, of course, and accessible via Ethernet. So this is what the custom resource would look like when you create the device model for that thing. So on the left-hand side, you can see that we have a device kind device model. We have one property for each of these channels. So you can see 2 here, but you would have like 0 to 7. And we specify the protocol, which is Modbus. And this protocol granted that you have a mapper that is registered to Edge core as Modbus. So you need like that translator running. And on the right-hand side, this is what you would find like the user guide, usually a PDF from the vendor, where you can find the Modbus register addresses for each of these channels. And we use that in our device instance. So it kind of tells the mapper where to go to get like sensor data for temperature sensor, pressure, or something like that. So for each of these properties, we specify the register address. You can do some more things like pushing data via MQTT or HTTP to edge applications, like we saw in the architecture section. And on the left-hand side, we have a device model ref to specify which device model to use, and config data on how to access that device on IP port in this case, because it's Ethernet. But now let's cross fingers and do some demo. I'm just going to describe a little bit what's going on before, and then you can just hope that everything crashes so you can have a laugh. So in this demo, we're going to demonstrate basic use of the KubeEdge stack with the Raspberry Pi. So as you can see it here, it is running. Yeah, the LED is green. And we won't have any visual feedback because we run this thing in a container, but you can run this Python app on your own laptop, and you will get something like this if you just raise your hands in front of your camera. So the way it works, it's a Python app that uses the Google Media Pipe framework. So this framework does multiple things. It can do like hand gestures, recognition, like facial expressions, but we are using the person posture. So you get like body points. It's automatically done, like there's nothing crazy about it. But the way it works, it extrapolates a shoulder line, and any hands detected above this shoulder line will be detected as raised. And that generates a data, like a data value. And that's what we see up there, raised hands value 2. So now, small caveat, because we have one shoulder line here, we're running like a crappy Amazon boats USB camera, and we have many shoulders in this room at different heights. So we're going to play a little bit with the first row, if you don't mind. And you will be our guinea pigs to try and make sure that we get something. So first of all, I'm going to bring up a terminal here. So I don't know if it's might need to zoom in a little bit.
Maybe a little.
So let's first take a look at the cluster. So here I'm running Kind on my laptop, and you can see the Raspberry Pi is running KubeEdge. So the first node is the Kind control plane, and the second node is our Raspberry Pi. So you can see that it has a different version. There's like a suffix, and we have a different role, which is Edge. But essentially, it's just like a normal Kubernetes node. So if I describe this node, you will find the exact same things you would find in like EKS. Like here we have this label I mentioned. We have an annotation for the cloud core address. But then you get the same like CPU request limits. We get like ARM64 architecture. So basically, our Raspberry Pi is just like there's nothing out of this world about it. So now I am first going to install the mapper, because if I look at the pods running in this cluster, we just have the basic pods. And I'm going to install that MQTT mapper. So the mapper is kind of forked from the upstream one. We've tweaked it a little bit. So let's install this. Now, It is running. Let's check out the logs to make sure that it has started. OK, looks happy. That's good. Now I'm going to install those custom resources, like the device model and the device. So let's do that just now. CRDs. We have one for the model that we installed first. And then we have one for the instance. And if I look at this, you might want to see what it looks like. So the device instance, like the model is not that interesting. The instance is called hands, because that's what we're talking about here. We have the protocol config data section that we saw earlier for that Advantech thing with an MQTT address. So in this case, we're using the embedded MQTT broker that is installed by the Edge core on the Edge device. Protocol name of MQTT, which is the name of our mapper when we started it. And we have an initial value of 0 raised hands because, well, the app is not even running yet. So let's install that MediaPipe app. And let's see if it started. So now the camera has started. The lights are blue. So it is running. And we are going to visualize this with a Grafana dashboard. Yeah, I need to serve the dashboard maybe first, otherwise I need to forward that port. Otherwise it's not going to work. Yeah, wrong kubeconfig. All right, 0 raised hands. So give me a raised hand. There's a slight delay because there's like a smoothing function.
Can we do it too?
Thank you.
I cannot see it. You have to tell me if you get to it.
It's changing, yeah.
Nice.
There's a smoothing function to avoid like flipping values. Otherwise, you would get like, it would go from 1 to 3 to 2, and it's kind of, so there's a bit of latency there. There are other reasons why we have latency because of the way we're displaying here, but it's kind of out of scope. Basically, this is just like experimenting a little bit with that. So I'm not going to get all the raised hands, so that's why we were thinking about maybe just playing a little bit with the front row.
How long is this cable?
I don't know if the cable is long enough. Maybe if
I'm not sure. You guys look very nice. Can you? Let's see. Does this work? Because I think the distance might be a problem for the camera because the resolution is low.
There's like a distance parameter because it's detecting like hands, fingers, and stuff. So
it might not be working that well right now.
You might need to go a bit closer.
Yeah, I'm just scared that if I actually go closer, everything is going to fall down. Maybe. Yeah. Okay, I have a theory. You guys are not the same height. That might be a problem with the shoulder. I've no offense. Okay.
Yeah, it's
okay. Just imagine the number changing. We could now ask a couple questions such as who is running Kubernetes at the edge in production, and maybe we could do a little poll, but also I would say Grafana is maybe not the best way of doing this, so you just have to believe it. You can tell everyone that it worked. Now, did you want to show a couple logs maybe? Like you could point it at me and show the logs?
Yeah.
Does that work? Can you help me? All right.
All right, so let's see if
let's
I put it
maybe
like
it
this.
recognizes me again. It did before, so maybe it works. Do we get something?
It's real finicky. Like,
I
think like it's not an industrial grade camera, so resolution is kind of a problem.
Yeah. Don't do this at home. Don't do this in the factory. Okay. Oh,
there you go.
Okay, it works. Show the logs.
So
don't move it. Show the logs.
I can't. So yeah, if I assume in this room you guys like black terminals, so I'm going to show you a little bit what this looks like in practice. So I'm going to zoom in a little bit so you can see what's going on. So the top left we have the KubeEdge custom resource, the device instance. So this is the value that we get in the Kubernetes API. So this is kind of the end of the chain. Top right, we have subscribed to the MQTT topic on the MQTT broker. So we are getting the value directly from the source because this is where that data is pushed by the app. And at the bottom, these are the logs of our mapper. So now, top left, it will change color just so you can see when the CR is updated, and you will see that there is a delay because that's like the edge core talking with the cloud core. Can you give me a second hand, maybe? We can get a value of 2. Okay, so you can see that there is a delay between the actual MQTT broker and the KubeEdge instance. I might be moving a little bit, so maybe that's why our MediaPipe app is a bit confused. So yeah, that's what we have here. You can have, we only have 2 values here, so we have the status of the hands device, and we have the number of hands. But think about an industrial device, like actual hardware, you might have a bunch of sensors, and so you could have like 8, 10, 20 different values going on there, which all depends on how the mapper is written. Yeah, I wish we could have gotten like more values here, but at least you see that it wasn't pre-recorded, let's say. But let's take a quick look at the setup, how this thing works behind the scenes. You might be familiar by now with this 3-layer diagram. So at the top, we have the cloud, which is the Kine cluster running on this laptop here. This is where the cloud core runs, and we have the Prometheus and Grafana stack. In the middle, we have the edge layer with that Raspberry Pi, and this is where the edge core lives. We also have the MQTT broker and the mapper over there. And at the bottom, we have the device, which, like the sensor or camera in like a proper context. Here, it's kind of the combination of the Python MediaPipe app and the USB webcam. So, to talk a little bit about the mapper itself, it is quite simple in how it works because it is simply subscribing to an MQTT topic on a mapper. Whenever it picks up a change of values, it will update the device in the edge core and expose that value on a matrix endpoint. And on the device side, on the Raspberry Pi, the MediaPipe app will process the camera stream. Whenever it picks up a raised hand, it will publish to that MQTT topic. So if you want to have a look at this repo where all this stuff exists, you have this QR code here with the mapper, the app, and the custom resources. And we're going to wrap it up real quick with a quick reality check.
Yes, so we're short in time, but really shortly, obviously you would not be running this in your factory. You could rather think of something like an AI model, maybe not detecting raised hands, but we do have a customer, for example, who does something similar to detect holes in paper production. Then I think another very important thing to notice is that instead of only using MQTT, you might want to translate from another protocol to MQTT and then maybe also do some local processing. Another very big difference is that you would never use Prometheus and Grafana for this kind of application. However, you might actually collect some time series data and put it in a database, and then maybe this could feed into some other IoT setup that you have in your factory or elsewhere. So the basic point of this demonstration is to show that, whereas it's a little silly, we still have each layer of an industrial-grade edge computing setup represented here, and the point of the edge is, in the end, to keep critical processing at the edge for low latency and resilience while syncing data to the cloud. Thank you so much for participating and listening to this and raising your little hands, even though it didn't work out as well as we had hoped. I'm not sure if we still have time for questions.
No.
Okay. no time for questions. Thank you so much.
Thank you. Thank you both. Thank you.
Oh, wow.
Oh, we are getting flowers.